Okay, so the recording has started now. So welcome everyone to the International Seminar on Automorphic Forms. Today we have the pleasure of having Rachel Newton from King's College London as a speaker, and her title is Evaluating the Wide Brauer Group.
Okay, thank you very much for the invitation and the opportunity to speak. I was assured by the organizers that it's okay if I don't know anything about automorphic forms. So I'll speak about my work with Martin Bright on evaluating the wild Brauer group. And please do feel free to interrupt if I get too fast at some point, or if you want to ask a question during the talk, that's perfectly fine. Okay, so as I said, this is about joint work with Martin Bright, and my setup is that L will be a number field throughout the talk, and X is a smooth projective, geometrically irreducible variety over L. Okay, and I'm interested in studying the rational points on X over L, and we usually do this by embedding them in the set of adelic points. So since X is projective, the set of adelic points is just the product over all the places of L of the local points of X over the completion of L at the place V. So if L is the rational numbers, we've got here the product of the real points with the p-adic points for all primes P. And this embedding is just because L sits inside all its completions. Okay. So in particular, if we have a rational point on X over L, then we have points everywhere locally, points over all these local fields. And in other words, we have an adelic point. And the interesting question is about going the other way. So if I have points everywhere locally, do I actually have to have a rational point on X? If so, then we say that the Hasse principle holds. So if having points everywhere locally guarantees the existence of a global rational point, we say the Hasse principle holds. So for example, the Hasse-Minkowski theorem shows that the Hasse principle holds for varieties defined by quadratic forms. Okay. But of course, the Hasse principle doesn't always hold. It can fail already for cubics. And so it's actually an interesting thing to study. And the Hasse principle is the first example of a local global principle that I want to mention. And the second example is weak approximation. So, I mean, when you study the rational points on a variety, the first and most basic question is, are there any? And then if there are rational points, you might want to know more, like how many are there? And one way of saying that rational points are somehow abundant is if a weak approximation holds. So if the rational points are dense in the set of adelic points. So this bar here denotes the closure of the rational points in the adelic points with respect to the product of all its local topologies. Okay, so if we're interested in rational points, we should be interested in these local global principles and when and why they fail. And one common way to explain the failure is with the Brauer group. So the Brauer group of X is this second étale cohomology group, but it doesn't matter too much for the purpose of this talk exactly what this group is, but what it does for us. Okay, so one of the key properties of the Brauer group is that if we have a local point on X, then we can evaluate elements of the Brauer group at the point, at this local point PV. And we land in the Brauer group of the local field. So what do Brauer groups of local fields look like? Well, they're actually quite simple. So at every finite place, the Brauer group of LV is just isomorphic to the rationals modulo the integers. So this the Hasse invariant gives this canonical isomorphism. Okay, so that's what happens if V is finite. What if V is an Archimedean place? Well, then the completion is either going to be the complex numbers or the reals. And the Brauer group of any algebraically closed field is 0. And the Brauer group of the reals is just cyclic of order 2. And I've written my cyclic group of order 2 here, not as Z mod 2Z, but as half Z mod Z, because I want to see it as sitting inside the rationals modulo the integers. And in 1970, Manin observed that you could sum up these invariants and obtain a pairing which takes in an adelic point on X, so a collection of local points, one for each place, and an element of the Brauer group. And the pairing spits out a number in the rationals modulo of the integers by summing up these invariants. So, the fact that this is actually well defined, that this is a finite sum, that's kind of in the content of this theorem of Manin. And the key point is that this pairing cuts out a subset of the adelic points which contains the closure of the rational points. So this superscript bra X denotes the adelic points which pair to 0 with everything in the Brauer group. Okay, and this is known as the Brauer-Manin set. So, so what if we have points everywhere locally, but nothing in the Brauer-Manin set? Then that forces the set of rational points to be empty. Okay, rational points are contained in this Brauer-Manin set, which is empty. So there's no rational points. And in this case, we say that there's a Brauer-Manin obstruction to the Hasse principle. So it's the emptiness of the Brauer-Manin set which is forcing the Hasse principle to fail. Okay, and the Brauer group can also obstruct weak approximation. So if the Brauer-Manin set is not equal to the full set of adelic points, then the rational points cannot be dense in the set of adelic points. Weak approximation has to fail because the closure of the rational points is contained in this smaller subset. So then we have a Brauer-Manin obstruction to weak approximation. Okay, so let's have a look a bit more about these evaluation maps and the obstructions to local global principles given by the Brauer group. Okay, from now on in my talk, I'm going to assume that we have points everywhere locally. Otherwise, we know we have no rational point and we can all go home. Okay, so now I'm going to use superscript A to denote the kind of Brauer-Manin set for A. A is an element in my Brauer group. The Brauer group of a smooth projective variety is torsion, so let's assume A has order n for some n. And yeah, so the superscript A is the set of adelic points which pair to 0 with A. Okay, so this contains the full Brauer-Manin set, the things that pair to 0 with everything in the Brauer group. Okay, so first observation. If the evaluation map is non-constant for some place, then A obstructs weak approximation. So I've written bars here around A just to make the distinction between A, which is an element of the Brauer group, and the associated evaluation map, where I just plug in different local points and evaluate A at them. And that gives me this map we saw before to the Brauer group of the underlying local field. And since A was assumed to have order n, I'll land in the n torsion of the Brauer group of the local field. And so what I'm saying here is if this is non-constant, then the kind of Brauer-Manin set for A, the points that pair to 0 with A, is not equal to everything. So there's something that doesn't pair to 0 with A. And then A obstructs weak approximation because, I said that this Brauer-Manin set for A contains the full Brauer-Manin set, because here we're just asking things to pair to 0 with A. The full Brauer-Manin set asks for points that pair to 0 with every element of the Brauer group. And that set contains the closure of the rational points. So in particular, the closure of the rational points is contained in this Brauer-Manin set for A. And so if these two sets are not equal, then the rational points can't be dense in the set of adelic points. They're contained in this smaller set. Okay. I hope that makes sense. We're going to see the proof anyway. So let's prove it. Okay, so to prove such a statement, so to prove that the Brauer-Manin set for A is not equal to the full set of adelic points, I just have to exhibit some adelic point which doesn't pair to 0 with A. So let's just take some arbitrary adelic point. That means a collection of local points. Okay, I might get lucky, and maybe this collection of these PWs pairs to something non-zero. So that would mean that this sum here I've written down would be non-zero, and I'd be done. If I'm unlucky and I happen to hit 0, now I can use the non-constancy of this evaluation map at the single place V. Okay, so I've got this sum which equals 0, and I want to destroy that equality. I don't want it to equal 0 anymore. Well, I know that at V, I can get at least 2 values, at least 2 different elements in this Brauer group of this local field, which means at least 2 different Hasse invariants. Hasse invariant was an isomorphism for finite primes and injection otherwise. Okay, so I can find some other point QV at the place V, which has a different Hasse invariant. And then, so if I replace PV by QV, I destroyed this equality. Okay, so non-constantly just at one place already tells me I have an obstruction to weak approximation. On the other hand, if my evaluation map has like the biggest possible image, so remember that, so let's take V to be finite here. So we know that the Brauer group of this local field is Q mod Z. And we know that A has order n, so we have to land in the n torsion of this Brauer group, which is something canonically isomorphic to the n torsion in the rationals modulo the integers. So that's 1 over n z mod z. Okay, so if my evaluation map hits all of those values, so this map is surjective, then A does not obstruct the Hasse principle. So by which I mean that the set cut out by A, so these are the elements which pair to 0 with A, is non-empty. So it doesn't give a reason for a lack of rational points. Okay, the rational points have to sit there. And we would say that A obstructed the Hasse principle if this set were empty, because it would be forcing a lack of rational points. Okay, and this is proven in much the same way, right? You take your sum, which is the pairing of A with your adelic point, and this time, instead of wanting to avoid 0, you actually want to get 0. You want to show that this Brauer set is non-empty. And then you can use the surjectivity at the place V to just adjust at that entry in order to cancel everything out and get 0. Okay, so you have enough freedom to do that. Okay, so I don't know how easy it was to follow these proofs. I don't think it's so easy to follow even simple proofs in an online talk, but that doesn't really matter. All I want you to take away from this slide is that sometimes knowing a lot about the evaluation map just at one place can tell you a lot about obstructions to local global principles. So understanding these evaluation maps is key. So that's what we're going to talk about in this talk. Okay. So now I want to move on to a question of Swinnerton and Dyer, which is asking which primes can be involved in the Brauer-Manin obstruction. Okay, so here's some notation and assumptions. S is a set of primes of L containing the Archimedean primes and the primes of bad reduction for X. And we're going to assume that the geometric Picard group is torsion-free. I'll explain about that assumption later, but it's a necessary assumption. So under these conditions, Swinnerton and Dyer asked whether there's an open and closed set, Z, inside the product over the primes in S, so the Archimedean primes and the bad primes. And, you know, any other primes that you decide to throw into S, but at least these ones. So it's a product of the local points at those primes, such that the Brauer-Manin set just looks like Z, product with, at every other place, the full set of local points. So that's asking whether the Brauer-Manin set only has conditions imposed on it at primes in S. Okay, so it has this kind of, this kind of quite simple shape. Everywhere else, it's just everything, and then only at these bad and Archimedean primes, or the primes in S, you have conditions. So this is essentially equivalent to asking whether outside of S all the evaluation maps are constant. And informally, we'll say that this is asking, does the Brauer-Manin obstruction involve only the Archimedean primes and the primes of bad reduction? Okay. Maybe those are the only ones that you need in order to describe your Brauer-Manin set. So why the assumption that the geometric Picard group is torsion-free? So Swinnerton and Dyer knew that you had to assume this. So here's an example where we have lots of torsion in the geometric Picard group, and the Brauer-Manin set certainly doesn't take the shape that Swinnerton and Dyer was predicting. Okay, so here we've got an elliptic curve over the rationals. Let's assume its Tate-Shafarevich group is finite and its Mordell-Weil group is trivial. Then the Brauer-Manin set just looks like the connected component of the identity in the real points, and everywhere else just the point at infinity. So this is like very small, right? Whereas this, when you don't have torsion in the geometric Picard group, Swinnerton Dyer is asking whether outside of finite set of primes, you just have the full set of infinitely many local points. Okay, so certainly this is kind of an example which should tell you that maybe you need to make this assumption. And in fact, Harari showed that, that if you have torsion in the geometric Picard group, the Brauer-Manin set is much smaller than this. Okay, so it's been proven by Harari to be necessary. Okay, so towards answering this question, Kolyatulin and Skorobogatov proved the following result. So with the same assumption that the necessary one, that geometric Picard group is torsion-free, and a further assumption that the so-called transcendental part of the Brauer group, which is the image of the natural map from the Brauer group to the geometric Brauer group. So this bar here is of course X considered as a variety over an algebraic closure of the base field. If this image is finite, then they show that the only primes that can play a role in the Brauer-Manin obstruction are the Archimedean primes and the primes of bad reduction that Swinnerton and Dyer predicted, plus possibly the primes dividing the size of that transcendental part of the Brauer group. But in 2023, so last year, the work with Bright was published, in which we showed that actually the answer to Swinnerton and Dyer's question is no in general. So we showed that under the assumption that X admits a non-zero global 2 form, then in fact every prime of good ordinary reduction is involved in a Brauer-Manin obstruction over some finite extension of the base field. Okay, so what do we mean more precisely? So with this assumption, if P is a prime of good ordinary reduction lying above a rational prime P, then there's a finite extension of the base field and a prime in that extension lying above the one you started with, and an element A in the Brauer group of X base change to this extension field who has order and a power of P, such that the evaluation map here is non-constant. And in the little observation that we proved, we saw that as soon as you have non-constant evaluation map at a single place, then you have an obstruction to weak approximation. Okay, so this already shows that the answer to Swinnerton and Dyer's question can be no, even for K3 surfaces over number fields, right? Because K3 surfaces satisfy this assumption. And okay, take a K3 surface over a number field and a prime of good ordinary reduction. Then after some extension of the base field, you've still got a K3 surface over a number field, and you have a prime of good reduction playing a role in the Brauer-Manin obstruction. And based on this work, Margherita Pagano gave the following example, which shows that, in fact, the answer to Swinnerton and Dyer's question can be no, even over the rationals. So our result involved a possible extension of the base field. So it was still open whether whether the answer could be no, just over the rationals without taking an extension. And so she wrote down this example. This is a K3 surface X over the rationals. Here's an explicit element of the Brauer group. So this is, an Azumai algebra. Think of it as a quaternion algebra of the function field, which actually belongs to the Brauer group of X. And she showed that here, 2 is a prime of good reduction, and the evaluation map at 2 is non-constant. So here, 2 is a good prime playing a role in the Brauer-Manin obstruction. Okay. So let me just say something about the assumption in our result. Why would you want to assume something like that? Or why should it make sense that assumption like this plays a role? Well, Hodge theory shows that H2 breaks up over C into these pieces in the Hodge filtration. Okay, and so this H02 being non-zero, okay, shows that this piece and this piece are non-zero. Okay, so B2, second Betti number, is the dimension of the left-hand side. And rho, the rank of the Néron-Severi group, well, the Néron-Severi group sits in this H11 piece. So this rho, this rank is at most this dimension. All right, so our assumption implies that B2 minus rho, so the dimension of the left-hand side minus the dimension of the middle piece, is positive because these two are non-zero. And why is that relevant to the Brauer group? Well, Grothendieck showed that the geometric Brauer group contains a copy of the rationals modulo the integers to the power B2 minus rho. So in particular, assuming that B2 minus rho is positive implies that the geometric Brauer group is non-trivial. And so, okay, these things are all defined over an algebraic closure, but we can take an element which is non-zero here. It's defined over some finite extension of the base field. And that means over that extension, the so-called transcendental Brauer group, so this image is non-trivial. Okay, and we need to have a non-trivial transcendental Brauer group in order to get an answer no to Swinnerton-Dyer's question, right? Because remember the result of Kolyar-Telen and Skorobogatov. They showed that the only primes that could play a role in the Brauer-Manin obstruction were the usual suspects, which is the bad primes and the Archimedean primes, and possibly the primes dividing the order of the transcendental Brauer group. Okay, but then if the transcendental Brauer group is trivial, then there's no primes dividing its order. And so their result, Kolyar-Telen and Skorobogatov's result, shows that the only primes that can play a role are the bad primes and the Archimedean primes. Okay, so we need some transcendental elements in the Brauer group. I guess that shows also that the A in our result is transcendental. Okay. All right. So having shown that the answer to Swinnerton-Dyer's question is no, so it's not only it's not just the Archimedean primes and the bad primes that can play a role. It's natural to ask, like, okay, but is there some finite set of primes that can play a role in the Brauer-Manin obstruction if we also fix the base field? Okay. So in our result, we showed all good ordinary primes play a role after some extension of the base field. But if we say no, we fix the base field, Margherita Bogano's result still shows that it's not just the primes of bad reduction and the Archimedean primes. She showed an example where 2 was a prime of good reduction and played a role. And in fact, we'll see that her result was optimal. So 2 was like the only choice. Okay, so so we're still under this assumption, which is necessary, that the geometric Picot group is torsion-free. And with Martin-Broit, we showed that the answer to this question is yes. So we show that there is indeed a finite set of primes outside of which all the evaluation maps are constant. And those primes are the following ones. So the usual suspects, Archimedean primes, primes of bad reduction. And then this third set of primes are primes with the following condition on their absolute ramification index. So that the absolute ramification index must be at least p minus 1, where p is a rational prime lying below frac p. Okay, so if p is a prime above 2, then saying that the absolute ramification index is at least p minus 1, that's just saying it's at least 1. Well, that's always the case. So this third set contains all the primes above 2. But for odd primes, it really is saying something. It's at least saying that the primes have to be ramified. And if your p is large, it's really saying it's like very ramified. And the fourth set is primes for which the special fiber admits non-zero global 1 form. And this fourth set is it's not needed if X is a K3 surface, and it doesn't contain any odd unramified primes. So if we wanted to, we could just kind of merge 3 and 4 and say we take all the primes above 2 and all the ramified primes. That would maybe be overkill, but would certainly still be a true statement. Because we're not actually saying that at these primes in S that the evaluation maps have to be non-constant. We're just saying outside of S, all the evaluation maps are constant, right? That means that if you want to understand the Brauer-Manin obstruction, the Brauer-Manin set, you really just have to play with each of these primes and figure out what's going on there. So let's see what this says for a K3 surface over the rationals. So in this case, the set of primes that can play a role in the Brauer-Manin obstruction are the infinite prime, 2, and the primes of bad reduction. So this is what I was saying about Margherita Pagano's result being optimal. She showed an example where 2 plays a role. Yeah, and that really was like the only kind of counterexample you could expect. Okay, so a counterexample to Swinnerton and Dyer's hypothesis. Okay, so how do you see this? So, okay, we've included the first 2 sets of primes, the Archimedean primes and the primes of bad reduction. The third set of primes, remember, was with this condition that the ramification index has to be at least p minus 1. But here we're over the rationals. Okay, so our absolute ramification indices are all 1. And for odd primes, we always have that 1 is less than p minus 1. Okay, so we don't have any odd primes in our third set. We just have to throw in 2. That's why 2 is there. And then if P is a prime of good reduction, then the special fiber is also a K3 surface, and K3 surfaces have no non-zero global 1 forms. Okay. Okay, so yeah, one kind of advantage possibly of our result is that we don't require the transcendental Brauer group to be finite. So in Kolyutin and Skorobogatov's result, remember that there was assumption that the transcendental Brauer group is finite. But it's still an open question whether the transcendental Brauer group can be infinite, right? So Skorobogatov and Zahin showed that the transcendental Brauer groups of abelian varieties and K3 surfaces are finite, but in general, we don't know. Okay, so in the second part of the talk, I want to kind of show you what went on behind the proofs of some of these results. And so this is a completely local picture because we're basically interested in showing, for example, that the evaluation maps that's at the primes outside S are constant. Okay, so we can just take one of those primes and we look at our variety X now over LV, so the completion of our number field at that prime. And we just want to understand what the evaluation map can be like. We want to show that it's constant eventually. So from now on, like let's let K be a p-adic field. So that could be our LV. And pi is this uniformizer, bold F is its residue field. And so now we're considering a smooth geometrically irreducible variety over K with a smooth model Kelly X over the ring of integers and special fiber Y, which we'll assume to be geometrically irreducible. Okay, so what do the evaluation maps behave like? So let's suppose we've got a p-adic point or a K point, Q, that extends to an integral point on the model, and let's call its reduction to the special fiber, so it's reduction mod pi, Q0. Then the following diagram commutes. So I'm writing P prime here to denote the prime to P torsion in the Brauer group. So remember that the Brauer group for us, it's a torsion group, and because X is a nice smooth variety. So here we've got our evaluation map. We evaluate elements of the Brauer group, elements of order K prime to P, at the point Q. And we land it in the prime to P torsion of the Brauer group of K. And we have these residue maps. So here's the residue map to H1 of the residue field of little k. And here we have H1 of the special fiber. And there we've got kind of an evaluation map at the point Q0, the reduction of the point. So this commutes. And okay, the key point that I want you to take away from this is that if I have an element in the Brauer group whose order is co-prime to P, then its evaluation at a K point, so K, I said, is a p-adic field, it's a finite extension of QP. Its evaluation at such a point only depends on what the point looks like mod pi, on its reduction to the special fiber. So that's great, actually, if you want to understand the evaluation map. You just have to do some computation over a finite field.
Why are we assuming prime to P torsion here?
Because it's not true.
Oh, sorry.
Yeah. So my next key point was this is no longer true for elements of order P or a power of P. Okay, so in order to evaluate a Brauer group element of order P at a p-adic point, it's not necessarily sufficient to know what that point is mod pi, or you might need to know what it is mod pi squared, mod pi cubed to some higher degree of p-adic accuracy. And the point is that this residue map here, the top one, we've got two residue maps. The bottom one is, this is just for a field, so that's fine. It's a local field. It's an isomorphism, in fact. The residue map on the top is not defined on the whole of the Brauer group. We'll see later that it's only defined on a certain piece of the Brauer group, which contains all the prime to P elements of order prime to P. So you can't even write down this diagram in general if you don't put if you try to put the full Brauer group here. There's no residue map. Okay. But we'll see a substitute for the residue map for those other elements of order P. Okay. So what we did with Martin was that we classified elements of the Brauer group according to the p-adic accuracy needed to evaluate them. And it gives a filtration on the Brauer group, which we called the evaluation filtration. Okay, so let's write it down. So essentially the nth piece in our evaluation filtration consists of elements whose evaluation factors through reduction mod pi to the n+1. In fact, we have to be a little careful here because there might not be enough points or something. So we really need this like overall extensions, overall finite extensions, or overall finite and unfinite extensions. But the moral definition is that the evaluation map factors via reduction mod pi to the n+1. And this numbering looks a bit funny, right? Like I start from -1 and then I have an n+1 here. Like, why didn't I just start from 0? But the numbering is chosen to match up with with Cato's filtration by Swan conductor. So just for ease of comparison later on. Okay. And so what happens when I take n equals 1 here, it's just saying, when I take n equals 0 here, it's saying factors modulo, it factors through reduction modulo pi, so reduction to the special fiber. When I take n equals -1, it's just saying that the evaluation map is constant. Okay, so that's one better than it's one better than the evaluation map only depending on what the point is, mod pi. It's like it doesn't depend on the point at all, it's just constant. So now let's introduce Cato's filtration by Swan conductor. But I'm not actually going to define it. But Cato's filtration by Swan conductor is defined on it's defined for Henselian fields. So we need to take a nice Henselian field which has some relation to R variety X. So here the Brauer group of X injects into the Brauer group of its function field, and then we take a Henselization of that function field, which is this capital K. In other words, it's the field of fractions of the Henselization of this local ring. All right. So Cato defined a filtration by Swan conductor on the Brauer group of capital K. In fact, he defined it on some more general cohomology groups, but we won't get into that. And so this N here is called the Swan conductor. Okay, so it's an increasing filtration. The smallest piece, the fil 0, the 0th part of the filtration, consists of those elements in the Brauer group which are split by an unramified extension. So this is exactly what you need in order to define the residue map. Okay, so there's a residue map which you can define on the whole of this fil 0. So for an element of order n, it goes here. And yeah, okay. In general, you can put Q mod Z here. So F here is the residue field of capital K, which is the function field of our special fiber. Okay. So this is like the largest piece on which you can define the residue map. So we could repeat the commutative diagram we had earlier for the evaluation, but with fil 0 instead of just the elements of order coprime to P. This contains the elements of order coprime to P. And so for the other, for the kind of larger pieces in Cato's filtration, there's no residue map anymore, but he defines the refined Swan conductor, which is this kind of description of the graded pieces in the filtration. So for n at least 1, he defines an injective homomorphism from the nth graded piece into the sum of differential forms. Okay, so if we have an element in our Brauer group, it's refined Swan conductor at level n. So, okay, so we had to have an element in the nth piece of the filtration. It has a refined Swan conductor at level n, and we write that as alpha comma beta. Alpha is a 2 form, and beta is a 1 form. This is over F. F, remember, was the residue field of capital K. Right, this is all a bit abstract. So let's do something a bit more concrete. Like, let's see what this looks like in a slightly more concrete setting. So let's suppose that we've got an element of order P in the nth piece of the filtration on the Brauer group of K. And let's assume that we've got P root of unity. So such elements can be written in terms of cyclic algebras. So this is a cyclic algebra. If P is 2, this will be just a quaternion algebra. So the nth part of the filtration, so Swan conductor N, corresponds to elements where that are generated by cyclic algebras where the first entry is congruent to 1 mod pi to the e prime minus n. E prime is P times the absolute ramification index divided by P minus 1. Okay. So in this setting, I can tell you what the refined swan conductor does. So at least, okay, let's do the example. So n is somewhere between 0 and e prime, and P doesn't divide n. There's other similarly explicit formulae in the case where P divides n and these other kind of extreme cases, but I just wrote down this one. It's the simplest one. Okay, so there is an isomorphism between omega 1 and this graded piece, which takes a 1 form. So I've got this 1 form here, x dy over y. So I can write any 1 form like that, and I map it to this cyclic algebra. Okay, the bars here are because x bar and y bar are in the residue field F, and x and y are arbitrary lifts of x bar and y bar to OK. So this is an isomorphism, and so I can then tell you what the refined swan conductor at level n of such an element is. So just, you know, if I started with a cyclic algebra like this, I can get this 1 form, let's call it gamma. And the refined swan conductor, gamma is a 1 form, so it maps it to d gamma, which is a 2 form, comma n gamma. So in particular, P doesn't divide n. P is the characteristic of my residue field here. So you can see that this map is injective, right? Okay. N is non-zero. And in particular, something we're going to come back to later is that if my refined swan conductor gets a 0 in the second entry, so if n gamma is 0, then in fact d gamma is also 0, of course. Okay, this will be important later, and I'll remind you at the time. Okay, so all right, so we've got this filtration on the Brauer group of this capital K, and we can use it, we can pull it back to get a filtration on the Brauer group of X. Okay, I just see where my element in the Brauer group of X lands under this map here. So I go to the function field, and then I've got a natural map from a field to its centralization, which gives me such a map. So our kind of main result is a comparison between our evaluation filtration and Kato's filtration by swan conductor. So it says that for n at least 1, the nth piece in the evaluation filtration, so those are the elements whose evaluation factors through reduction mod pi to the n plus 1. So that coincides with elements in the nth plus 1 piece of Kato's filtration whose refined swan conductor at level n plus 1 has a 0 in the second entry. Okay, and then at level 0, they're equal on the nose. So fill 0, that's the thing split by an unramified extension where you can define a residue map that coincides with exactly the elements whose evaluation factors via reduction to the special fiber. And that's exactly to do with this commutative diagram we had. You can where your evaluation only depends on the reduction of your point to the special fiber using the residue map. Okay, and then the minus 1 piece, remember that's the things with constant evaluation. Those are the things whose residue map is constant. Remember, in general, the residue was landing in H1 of the special fiber, and here it's just in H1 of F. F is just a finite field. Okay, it's the residue field of little k, which is a p-adic field, a finite extension of p-adics. So this is really just something constant. This is not to be confused with the function field. So, okay, so I said we had this like funny numbering, right, where we start from -1. And then, the fact that our 0 matches up with Kato's 0 is nice. But in fact, this nth piece, most of the time, it actually matches up exactly with Kato's n piece. So this thing on the right-hand side is usually just equal to the nth piece in Kato's filtration. So here I claim that the nth piece in Kato's filtration sits inside this thing, which our theorem says is equal to the nth piece of the evaluation filtration, with equality as long as P doesn't divide n plus 1. So most of the time, phil n and ev n are equal. Okay, so let's see that. So remember, we have this refined Swan conductor, level n plus 1, which is an injection from this graded piece to this sum of differentials. Okay, so in particular, if I start with something in the n plus 1 piece of the filtration, and I want to prove it's in the nth piece, that's equivalent to showing that its refined Swan conductor at level n plus 1 is 0. Okay, this is an injection on that graded piece. Okay. So in particular, okay, by the nature of this map, everything in phil n has refined Swan conductor at level n plus 1 equal to 0, 0. Okay. So in particular has 0 in the second entry, and we have this containment. So that's this containment that I stated in this claim. And now I just have to do equality if P doesn't divide n plus 1. Okay, so I have some refined Swan conductor, it's alpha comma beta, and I claim that if P doesn't divide the level at which I'm taking the refined Swan conductor, then as soon as beta is 0, it implies alpha is 0. So I haven't really proved that, but at least in this case, okay, now I have to take n equals n plus 1. Here, it's just saying P doesn't divide the level at which I'm taking the refined Swan conductor. So this is what I was saying, that, if P doesn't divide this level, then as soon as this second entry is 0, the first entry has to be 0 as well. Because gamma is 0, so d gamma is also 0. So when P doesn't divide the level, the only way I can get beta being 0 is if alpha is also 0. And that's why then this is equality, because having them both equal to 0 is the same as being in the nth piece.
So that previous slide proves what you're saying in case it's generated by cyclic algebras,
Yeah,
right?
yeah.
What you said is true if K contains a p-th root of unity, but you're not assuming this here.
No, and I'm not going to prove it in generality. But we do have, in general, the formula. So here, d gamma was my alpha, and n gamma is my beta. So hang on. So alpha is d gamma and beta is n gamma. So what's the relation I get then? I get that d beta equals n times alpha, right?
Mm-hmm.
And that relation is always true.
Mm-hmm. Uh-huh.
So if I always have that, let's go back here. If n times, well, it would be n plus 1 here, right? When I was saying n, it's like the level at which I'm taking the refined Swan conductor. So if my relation here would be d beta is n plus 1 times alpha. So if beta is 0, then d beta is 0. So then I get 0 equals n plus 1 times alpha. And P doesn't divide n plus 1 is necessary here because I'm in characteristic P. So then I find alpha is 0. So yeah, and Kato proved this relation, this d beta equals n alpha. Or at least we're able to extract that from he didn't write it quite like that, but he did prove that. All right, so how did we prove this comparison result? Well, yeah, we had to understand exactly the variations of these evaluation maps on p-adic disks. Okay, so we define this kind of p-adic disks. So here's a point, an integral point on X. And so BPN is the points which are congruent to P mod pi to the n. And we showed that if we have an element in fill n, so it's the nth piece of Curtis filtration, with refined swarm conductor at level n equal to alpha comma beta, then the evaluation map varies linearly on this p-adic disk and is controlled by beta. Beta was the swarm form over function field f, beta p0. So p0 is the reduction of p to the special fiber. And if beta equals 0, then we get something slightly more complicated. So we actually get that the evaluation map is constant on this disk, but varies quadratically on some larger disks. And the quadratic variation is controlled by the alpha 2 form. So I'm not sure whether I should say more. Let me write down this last thing. So more precisely, if I have some point in this disk, so it's a point which is congruent to P mod pi to the n. Let's take some coordinates and write Q as P plus pi to the n times some vector. And then we'll consider that vector mod pi. So that's something in the tangent space, special fiber at the point P0 that was a reduction. Then we have this nice formula for the evaluation, or for the Hasse invariance. So if we take the evaluation at the point Q and take its Hasse invariant, then that's equal to the Hasse invariant at P plus this trace. So this is take beta at P0, okay, that's some one form that I can evaluate at this vector in the tangent space to the special fiber, and then I can take this trace. I mean, okay, yeah, I've realized that I was putting my Hasse invariance in Q mod Z, right? So I should put a 1 over P here. So this trace is going to be something in FP, so in Z mod PZ. Really, I should remember that I don't want to write things in Z mod PZ. I want to write them in 1 over P Z mod Z. But I hope you forgive me for that. Maybe I should write 1 over P here. It looks a little confusing to divide something in characteristic P by P. That's actually how we wrote it in the paper, though. But I mean, the key point here, or a key point here, is that if beta is non-zero at point P0 and we have an element of order P, then this evaluation map is surjective. It takes P values, okay, because this part here can take P different values. As soon as we get something non-zero here, we can pair it with different vectors and get all P different values for this trace. And there's a more complicated formula for the quadratic variation when beta is 0. I don't know whether I should stop here. I've only got 4 minutes remaining. So I was going to say something about this proof, but maybe I will just stop here and ask for questions.
Okay. Okay, thank you very much. So maybe let's first thank Rachel for the talk. I'm also going to stop the video